So this is our bar element here, oriented in the global coordinate system. So let me introduce the axis. This axis here, maybe I should draw a straight line. So this axis here, this is our axis, one axis there. And then we have the horizontal axis, right? So this is our arrow, this is Y, this is X. Maybe I have started with the overall, but I hope you not be lost. Again, if we had started with this, already the X-axis is indicated. For the local coordinate system, the X-axis or the X coordinate is given and the Y coordinate is given. Of course, remember why the Y is like this is because of course the Cartesian plane, the angle is they are orthogonal to each other, the axis. So now here I have introduced the global coordinate system. So what we want to do is we want to resolve to see the transformation. What does it take, or what do we need to do to transform the axis? Because once we transform the axis, we can be able to transform the nodal displacement from the local coordinate system, the u prime I to ui. And we know that this axis here, this represents the vi at the global coordinate system, and this represents the ui at the global coordinate system. This here is ui prime. In this case now here, the vi prime, which we are saying at the local coordinate system might not make sense to you for now, is there. So let's consider just this node I. Node I. This is node J or node 1 or node 2. So at the local coordinate system, when we are just considering one element, there is no vertical displacement at the node. So that's why we are saying this v prime I or v prime j does not contribute to the stretch of a bar element, stretch or deformation of a bar element, but it contributes to the deformation of a structure. All right, now we have done that. So what we need to do here, we are going to employ the issue of similar triangles. So if this is this angle is given theta, if I make a right angle here by drawing a straight line, you make a straight line anywhere. It's not, remember, you're not concerned with this node J. Yeah? We are considering node I. So let me just make a right angle here. I want to make this right angle here, so that I want to use similar triangles, and again the issue of right angle triangle, and then use this principle. I hope you remember it. So katoa. Okay, the sine, cos, and the tangent. So again, I can stretch this. This is theta. This angle is theta here. This angle is 90 minus theta here. I can extend this line to meet my y-axis in that point. Okay. Now, from a similar triangle, even you can use simple geometry, high school geometry. If this is 90, is this theta, this is 90 minus theta. Remember the bigger triangle here, this is a right angle. And we are saying this is 90 minus theta. This is 90. So the angle here is theta. Okay. So let me remove this. Okay. So we are left with this angle here. This is theta. So why am I concerned with this? Because I know VI, I know UI prime. We are not concerned with the J, the known J. So I know VI, the overall, the global. I know at the global coordinate system, the vertical displacement is along the y-axis, and I know the horizontal displacement along the x-axis. So I have I know vi, I know ui at the global scale. I am given at the local scale, local global coordinate system. I know ui and I know vi. So because I know these sides, why I was extending this angle is because I want to use these triangles. So I don't know these sides. I don't know this side, and I might not need them. So when I look at this angle theta, and I see this value here, this is, remember, this is a correction here. This is not a local coordinate system. At the local coordinate system, ui is given, it's along this element. This is at the global. This is at the global. This is the one at the local coordinate system. This one here. So I want to transform this ui to u prime I to ui. So you see, this is a right angle triangle. I know the adjacent, I know the hypotenuse. So what do I need to use? Cos. So cos theta, in this case, is equals to adjacent, which is equals to u prime I over hypotenuse, which is ui. So, and in that case, I'll have u prime I, because we want to see the transformation, is equals to ui cos theta. Okay, so it means to move from the local coordinate system ui, I need to multiply with the cosine of this angle. I have resolved it along the horizontal axis. So how do I resolve it to the vertical axis? So that's why I had to extend this triangle here. So that now I have this angle theta. I know now this is a right angle triangle because this one was 90. So of course this one is 90. This is a straight line. So I know what is the opposite. The opposite here is ui. The adjacent is the hypotenuse is vi. Adjacent here is not known. So I don't need the adjacent. I need to use the hypotenuse and the opposite, which is sine. So again, we can say sine of this theta here, sine theta is equals to opposite, which is u prime I over vi. And this one gives me, so this one will give me, let me show you something we can do here. So because we already have calculated this, we already see that. So this one again, now I can move it here. So we are saying ui is equals, u prime I is equals to ui cos theta. And from here, you can see, again, when dissolved in the vertical axis, ui prime is equals to vi sine theta. So far, so good. Very simple. Now we have resolved from local coordinate system for the horizontal displacement, or the displacement, not horizontal, sorry, displacement along the axis of the element. We have we have been able to resolve this displacement along that direction. So the other thing that we need to resolve is this displacement here. Remember, at this point, it might not make sense at the element scale, but at the global scale, we know the vertical displacement for the structure is important. Why we are saying it doesn't make sense because it doesn't contribute to the stretch of an element, because the load is only applied at the axial, along the axis of the member. So now here, again, what we need to do is we need to use this. We are utilizing this, the known values, the theta and the ui prime and the vi prime and the vi that we know and the ui that we know. So in this case, we can extend the axis, the horizontal axis in this direction. And remember now, when we extend in this direction, the signs are very important. So here you'll have negative u I. The same case, if we extend it downward, it will be negative. So now from this point, we need just to use a simple triangle, a similar triangle the way we have this on this side, and then simple geometry, we can be able to calculate or to obtain, to resolve the forces, the displacement on the vertical axis. We want to resolve in this axis. We want to resolve the vertical displacement in the local coordinate system to both vertical and horizontal in the global coordinate system, resolving forces. Now, what we do here is, again, we draw okay, let's see, how do we get an angle on this side? Because we are not given, here we are not given any angle. We might say we don't have any angle here. So what I can do here, let me extend this again. I said this one, you have to work it out. I hope you are working together with me. I hope you're not just watching me. I've just extended that. And then what I can do is, I can have another line here, similar triangle. If I do a line parallel, if I plot a line parallel to this, to the element, our element is oriented here. Remember, if you see that this line is parallel to this line. So if this axis, I can draw another parallel line to the x-axis of the local coordinate system here. Let me draw using a straight line. So I plot it here, touching both the y and the x-axis. It doesn't look so parallel, but I hope you understand what I mean. So you put it, maybe it's more inclined like that. Okay, so that this now is parallel to, now this one is parallel to this axis here. Okay, and the first one here, we said this one is parallel to this one. So with this, remember, this angle is 90. This angle is 90 here. Between, of course, the y and the x at the local coordinate system, this is 90. And we said this angle is theta here, and this whole of this angle is 90. So this angle is 90 minus theta. And if this one is 90, then this means this is theta. So this angle here, this angle here is theta. And now our work have simplified because this is a right angle. This is right angle here. Let me use a highlighter. Now this is right angle here. Then this meaning this angle is 90 minus theta, and therefore this angle is equals to theta. Okay, this angle here is equals to theta. So you see, we have utilized the geometry you learned, and then we are just getting the different angles so that we can be able to resolve our forces, our displacement, nodal displacement. So if you now with this triangle, without even doing much, you can resolve, like we want to resolve this now, v prime I in this, in the horizontal axis. So we know we have this angle theta, and we have this is right angled here. So we have the opposite, which is v prime I, and we have the hypotenuse, negative u prime, no, ui. So you use sine. So you say sine theta in this case will be equals to v prime I over minus u I. The same case, if we want, okay, now here you can see we have resolved this v prime I in the global coordinate system, the horizontal, we have gotten the horizontal component. Same case now, to get the vertical component, we have this angle. This is right angle triangle. We know this value. This is what we want to resolve. We know this is VI. So we have the adjacent. We have the hypotenuse. So we use cos. So cos theta will be equals to V prime I over V I. So in short now here we can, so okay, let me just write here without erasing that. So here we can have now, use a thicker line. So if we make V prime I, so here we have V prime I to be equals to, that's too thick. V prime I, remember this is prime, V prime I will be equals to VI cos theta. And from this one, we have V prime I will be equals to minus UI sine theta. I hope we are together up that point. I hope you have not lost anybody. So we have utilized the causes, we have utilized the sines. So let me just move them back here. Let me move this one back here. So with the VIs, let me rewrite them here. The V prime I, I'm just transferring this one here. So this will be VI cos theta. Now the V prime I again is equals to minus UI sine theta. So in overall, we can use this. Use this space. So the resolution or resolving U prime I to global coordinate system is a combination of these two. UI cos theta plus VI sine theta. And the same, the V prime I is a combination of, so V prime I will be equals to VI cos theta plus or minus, this will be minus UI sine theta. So this is what you have in your note. So you don't have this derivation. And I hope you can be able to follow it the way we have derived simply. So now you can now go ahead, start writing this in matrix form. If you write this in matrix form, you'll have UI, U prime I, V prime I. This is a vector of nodal coordinate, the coordinate system. So this will be, so you can put UI here at the end. UI in the global coordinate system, VI. This is a vector, was vector. Now this one will be cos theta, sine theta. Now remember, this is V, this is U, so you need to interchange so that the UI and UI becomes fast, and therefore you have sine theta, negative sine theta, cos theta. And this is now how you transform the nodal coordinate system from the rock coordinate system, the nodal coordinate from the rock coordinate system to global coordinate system by pre-multiplying with this transformation matrix. This transformation matrix for a single node, remember it's node I. So for a single node, we are saying capital T. For a single node, we use that with the line there or the tilde mark so that we denote that is This is the matrix. This is a transformation matrix for a single node, node I, or one node. So you can do the same for node J here. Nothing changes. Just transform. You just shift these angles there, the triangles, and then you do all that stuff. So sometimes you may find, like in many books or many lectures, you're just given what is the transformation. But I feel as engineers and of course as scientists, and because you have covered this, I like the derivation part of it, so that you know where we are coming from. You can be able to relate, to have a feel of where did these figures come from basic principles, so that you can appreciate the workings. So this is the transformation matrix for the nodal single node. We use a tilde there, and then so here we can write in compressed format. You say this is U at the local coordinate system. So U prime there, and then here V U at the global coordinate system. This is a prime here. So this is the equation for transformation. To transform from a local, you pre-multiply with the transformation matrix to get the global component. All right. So I want you to digest that, because I'm going to the next slide, and this information is going. So you can take a screenshot if you, oh no, you can still come back to this video later on. So let's now move here. So the transformation. So right, before I move from this, we said for a single node, we have seen for a single node, the transformation matrix is equals to, this is cos, sine, minus sine, cos. And these cosines and sines, these are what we call directional cosines. Now I know some of you now are already wondering. We have gone back to, is it calculus 4? Directional cosines. Okay. And sometimes they are written in short form. You may find that you can write in cos, or they are abbreviated as L for cos and the M for sine in some books. I also like to say, instead of writing cos, I just like C, and sine it just like S. Now with this, for this single node, now we want to see for the overall node. So this one will be the same even for node J. So UI, that UJ, the transformation matrix is the same. To get the overall transformation matrix for one element, so we do like this, or we have something like this. This is UI. Remember, this was UI, VI, UJ, VJ. We have introduced something here. This is what I was saying. You can use a pencil there to demarcate. Okay, so that we are going to fill these cells. We are going to fill the cells like that. UI, VI, UJ, VJ. And for the two nodes, remember the node 1, the one that we just derived, was node I, and we found that U prime I, V prime J, or even without repeating this, I can just come here and write U prime I, V prime J, V prime I is equals to this, and then we have UI, VI. So what does this tell you? This tells you that here we can say, of course, this is UI, and this is VI. Same case for the second node. You have uj prime, vj prime being equals to the same, this matrix, the cos sine minus sine cos, then uj vj when you do that derivation. Okay. So, and then this will be uj vj. So to fill these cells for the overall for one element, we want to get what is the transformation matrix for a whole element, for a two node element, bar element. So you just need to superimpose ui, ui. You come here, you have ui, ui, this element. But when you come here, you have this is uj. So this one relates j, this one relates I. So by just observation, you can see that the two are not connected. They are not related because they are not at the same node. Okay, it's not the same node. So you see where we have ui, this one you can fill directly. Ui, we have is a cos. Vi or vi, ui is a sine. The i's are related by themselves. Ui, and vi, so is this one. But we know there's no relation between j and I. They are not integrated. So this one becomes zeros. Same case, i's and j's have no relationship. So this one 0, 0. And finally, jj, uj, vj, uj, vj is this one. Cos sine minus sine cos. So that if you look carefully, the overall or the transformation matrix for the whole element, for the two node element, this T here, we call it capital T. And remember, for a matrix, we use this for a square matrix. So if you look at this, you can see similarity here. There is this part, and it's the same part here. And then these ones are zeros, zeros. So this one will be composed of, that is the transformation matrix for each node, T, 0. Okay, we no need to, because we are already inside the matrix, no need to use this. So that will be the transformation matrix for each node, T, 0, 0, T. Where this is the first one is transformation for node I. This is the transformation for node J. So this is the transformation matrix for the element. Not just one node now. This is for the overall element. And now if you want to, which I was giving in the next slide, if you want to now show the equation, now here I've just moved very fast. If you want to show the equation here, you just need to introduce the force vector, the nodal vector from the local coordinate system, that is u prime I, v prime I, u prime j, v prime j. Then this is the matrix, the transformation matrix, capital T. This is why I was saying this is the transformation T tilde at the nodal transformation matrix, which is the same as here. The rest is 0, 0. And then we have the nodal vector at the global coordinate system. So this is the transformation. So from the local coordinate system, you don't have to say prime, because you don't have to say I, because we are saying for any node. So that one will be u prime. To get to global coordinate system, you pre-multiply the nodes at the local global coordinate system with a transformation matrix. Now, for the whole element, we have removed the tilde, the mark that we are putting here up. We have eliminated it. So that's how we transform from local coordinate system to global coordinate system. We have been able to transform the nodal displacement. Same case if we want to transform the nodal force, F prime, to global coordinate system, F we just need to pre-multiply with this transformation matrix. Okay, like that. Anything from local to global, this is the transformation matrix that we use. So all quantities in the local coordinate system, be it displacement, be it forces, be it, we are going to see also the boundary condition you can be able to transform, can be transformed using the transformation matrix and these relations, which are very important. Now we have seen the transformation. Let's now move to the next stage very fast, because the other part, I think they are not very new. It's about how do we get the equation, or how do we get the stiffness matrix. So this is just a repetition of what I have just explained, that you can transform anything from local to global using the transformation matrix. And the transformation matrix for an element we have seen is a combination of the transformation from for one node and another node. All right. Same case, nodal force can be transformed